Section 7. Kinetic Molecular Theory and Graham's Law. Chem Talk. Molecular size and molecular motion of gases. Kinetic molecular model of gases. Scientists have adopted the following model for gases. Gases consist of tiny particles, atoms or molecules, that are separated by relatively large distances. For water, the particles are about 1,000 times further apart in the gas phase than in the liquid phase. Gas molecules are in constant random motion and travel in a straight line between collisions. They do collide frequently with other gas molecules and with the walls of their container. Gas pressure is related to the sum of all these collisions with the walls during a given time. At any given temperature, Kelvin scale, the average kinetic energy of all the molecules of gas is directly proportional to that temperature. However, some of the molecules will be moving faster than the average, some slower. At the same temperature, all gases have the same average kinetic energy in their molecules. As the temperature increases, so do the average velocities and kinetic energies of the molecules. Dalton's law of partial pressures. Because gas molecules are so far apart, all gases behave the same way at ordinary temperatures. This is stated by the kinetic molecular model of gases, in which the properties of gases are discussed and, regardless of the gas in question, the properties are the same. John Dalton recognized this behavior and, in 1801, proposed that in a mixture of gases, such as air, the total pressure exerted by the gas mixture can be found by adding the pressures exerted by each of the gases in the mixture. Mathematically, this is expressed as example. For air, total pressure equals the pressure of nitrogen plus the pressure of oxygen plus the pressure of argon plus and then the total pressure of air will equal 760 millimeters mercury at standard conditions. Diffusion. When the perfume or other odors left the bottle and traveled about the room, you observe that the students closest to the teacher smelled the perfume first. Diffusion is the spontaneous mixing of one gas or liquid with another that occurs because of the random movement of the molecules. This occurs with perfumes because the fragrant gaseous molecules move freely through the widely spaced air molecules to reach your nose. In typical classrooms with radiators, air conditioners, open windows, students moving around, etc., convection currents are much more important in distributing gases than diffusion. The process of diffusion is complete when the molecules of the gases are evenly spread within the room. Diffusion is purely a physical phenomena. The rate of diffusion has to do with the speed of gas molecules. All gases at the same temperature have the same average kinetic energy. However, gases with a large molar mass have slow speeds, while gases with a small molar mass have fast speeds. The velocity of a gas molecule is related to its kinetic energy. Kinetic energy equals 1/2 molar mass times velocity squared, where m is the mass of the molecule. Since two gases have the same kinetic energy, you can derive the relationship from the above equation. Assume that you have a gas with a large mass and one with a small mass. Since their kinetic energies are equal, you have 1/2 the mass times the velocity squared equals 1/2 the mass times the velocity squared of the gas with the smaller mass. Okay, and then these are inversely proportional to the square root. The velocity of large mass gases is smaller than the velocity of small mass gases, and its diffusion is also slower. For example, if the ratio of the masses of the gases is 1 to 9, then the ratio of speeds will be 1 to 3. If you make the mass of the particles 9 times larger, the speed decreases by a factor of 3. Effusion. When the balloon deflated over time, it was because the interior gas was leaking through tiny openings in the balloon latex. These holes in the material are molecular in size and much, much smaller than a pin puncture would be. The effusion of a gas is its movement through tiny holes from a region of higher pressure inside the balloon to a region of lower pressure outside the balloon. Even though the hole in the latex that they escape from is microscopic, it is still much larger than either of the gas molecules. A smaller molecule, such as H2, effuses faster than a larger molecule, such as carbon dioxide. In addition, even though the two kinds of gas molecules have the same kinetic energy at the same temperatures, the hydrogen has less mass, which gives it greater speed. The major reason that hydrogen effuses faster than carbon dioxide is that it strikes the inner surface of the balloon more frequently, giving it a better chance of hitting one of those tiny holes. A Scottish scientist, Thomas Graham, studied the rates at which various gases effused through a tiny hole. He found that the higher the density of a gas, greater the mass, the more slowly it effuses through a hole. He was able to develop a mathematical expression for the effusion of gases now called Graham's law of effusion. It is very similar to the expression for diffusion, and it is usually used to compare two different gases. Graham's law states that the rate of effusion of a gas is inversely proportional to the square root of the density of the gas. Since equal volumes of gas at the same temperature and pressure contain equal numbers of gas molecules, the rate of effusion is also inversely proportional to the square root of the molar mass of the gas. The gas with the lowest molar mass effuses the fastest. Once again, since the kinetic energies are identical, 1/2 mass times velocity squared equals 1/2 mass times velocity squared. And then here's your inverse proportion where it's flipping. See how it's the S and the L are flipped, and there's that square root, that meaning that it's inversely proportional to the square root. Look at the velocities of the two gases in the investigation, hydrogen and carbon dioxide. The molar mass of hydrogen is 2 grams per mole. The molar mass of carbon dioxide is 44 grams per mole. What is the rate of effusion of hydrogen to carbon dioxide? So here's the rate of effusion. So you're taking the velocity of hydrogen divided by the velocity of carbon dioxide, and then you have the square root of 44 grams per mole over the square root of 2 grams per mole, and then you have your rate of effusion. Solving the equation gives a ratio of 4.7 to 1. This tells you that at the same temperature, hydrogen molecules have a velocity 4.7 times greater than carbon dioxide molecules. It was the higher velocity that allowed the hydrogen to leave the latex balloon faster than the carbon dioxide. A practical application of Graham's law is the separation of isotopes of uranium in the enrichment process. U-235 is needed for making nuclear fuel and atomic weapons, but it makes up only 0.7% of natural uranium. The other 99.3% is U-238. Scientists developed a process in which uranium hexafluoride, UF6, is enriched in the lighter isotope by effusion. And remember the formula for effusion. Okay. And solving this gives you the rate of effusion, but you could substitute, if you know the molar mass, of different elements and different compounds, then you just enter the molar masses. These would be the molar masses entered in here. And then you get the rate.